So, good morning everyone. So, in today's lecture I am going to continue our discussion on the Hamiltonian formulation of the condition for finding the extremals. So, we will continue our discussion on the Hamiltonian formulation. So, this is a continued series of discussion. Okay, so I am going to start our discussion right away by introducing the Hamiltonian formulation for functions of several variables, right. So, that will include the special case of function with one dependent variable. So, several dependent variable case, right. So, I am talking about, so let us consider a Legendre transformation involving the Lagrangian of the form L of t comma q bar dot, where my vector q bar is q1, q2, qn, right. And so, we will see that we are going to, so again if our starting function is of this form, the first set of steps for defining the Legendre transformation is to introduce new sets of variables. So, my so let me introduce the new variable p. So, let my pk, the variable pk, be defined as del L del qk dot, where k is from 1 to n, right. So, I define my variables this. Let me call this definition as 1, right. So, this is my my variable p. Now, we can also, using this one, we can invert this relation to find qk in terms of pk, provided this inversion is possible. What I mean by that is certain higher derivatives are non-zero. So, 1 can be used to solve. So, it can be essentially inverted, solve for qk dot in terms of pk, provided the Hessian matrix has a non-zero determinant, where the Hessian matrix M is described by del partial to partial L of partial qi dot qj dot. So, this is my ijth element, right. So, this Hessian matrix is non-singular, or it has non-zero determinant. So, right. So, this is the standard inversion argument for functions of several variable. Now, so first we are, so next we have to define another variable, which is our Hamiltonian variable, right. Now, note that while introducing the variables p and h, we have used the fact that t and q are passive, right. So, let me now introduce another variable. Let the n dimensional Hamiltonian is defined by h of t comma q bar comma p. So, instead of so now this is with respect to these variables, is defined as described in our towards the end of our previous lecture, is minus L t comma q bar comma p bar, right, plus summation qk dot pk, right, k from 1 to n. So, n variable setup, n component setup. Okay. So, in the, I call this as my definition 2. Okay. So, in these two definitions, I have assumed that the variable t and q bar are passive variables, that is they are going to appear implicitly. Essentially my new variables are p and h. Okay. So from here I can quickly check that this Legendre transformation, so this is my Legendre transformation. So this Legendre transformation defined by 1 and 2 is an involution. So the first statement that I want to show is 1 and 2 is a Legendre transformation which is an involution, Legendre transformation which is an involution, right. So let me show it how. So again we take the derivative of the Hamiltonian with respect to p. So note that dH dpk is by definition, so p appears both in L and the second term. So this is going to be summation j from 1 to n, and then this becomes minus partial L partial pj, right. Well, this is partial L partial pk, and then from the next term I get plus summation of qj dot, so partial qj dot partial pk, where j is from 1 to n, right, times pj plus the second variable is will be qk plus qk dot. So I am using the product rule. Note that I am using the product rule here in the derivation, in the differentiation of h with respect to pk. Here I am using the product rule. Okay. So now I can further use the chain rule that this is also equal to summation partial L partial q partial L partial qj dot times partial qj dot partial pk summation over j. So finally, using all these relations, I can find that del h del pk is the summation j from 1 to n of minus del L del qj dot plus pj of partial qj dot partial pk, right, plus qk dot. So del L del qj dot plus pj times this, and notice that this is the definition of pj. So pj is by definition del L del qj, so this is equal to 0. So I see that this is also equal to qk dot, right, and also notice that minus of h of t comma p comma q comma p plus summation qk dot pk, by definition of the Hamiltonian this becomes L of t comma q comma p bar. Okay. So these two relations show that the definition of p and h to my older variable t and q bar is an involution. So this Legendre transformation is an involution. Okay, or one is the inverse of the same map is the inverse of itself. Okay, so then so let's look at this example in a more more applied framework. So for example, in Newtonian mechanics, my L, which is the Lagrangian, is the sum of the kinetic plus potential energy. So in Newtonian mechanics, My pKs are denoted as the generalized momenta variable, okay, and my L which is the Lagrangian, my L which is the Lagrangian, right, is defined to be T of T comma Q bar dot minus V of T comma Q bar, where the first quantity is in the continuum mechanics is the kinetic energy and the second quantity is the potential energy, right. So this is the sum of the kinetic energy and minus the potential energy, okay. Okay. So then and finally my vector q is the position of the particle at time t, So for example, consider a freely moving particle of mass m. Consider a freely moving particle of mass m if I am given the position vector q to be q1, q2, q3, freely moving particle of mass m with the position vector this, and these are my Cartesian, for example, these are my Cartesian, the Cartesian coordinates of the position of the particle, right. So consider a freely moving particle, and in this case my so which means that in this case my kinetic energy T of q comma q bar dot is given by the following expression: half m v square, which is half m q1 dot square, q2 dot square plus q3 dot square, okay. Here I am not given any information about the potential energy, so let me assume that this is 0, right. So we see that my pk, the generalized momenta, is del L del qk dot, which is also equal to m qk dot by the definition of L. And finally my my Hamiltonian will be so my H is equal to minus T, which is the kinetic energy, plus summation qk dot pk, okay. So these are my new variables in the Hamiltonian formulation for this example, okay. So let me call this as example 0, right, and we can extend this example for j identical particles. So for j identical particles I can write down the same Hamiltonian, j identical particles for each particles. So I have that n this time becomes 3j. For each particle we have 3 coordinate positions, and hence we have the total degrees of freedom being 3j, okay, and where j is the is standing for each particle, okay. So then let us now, so we are now in a position to describe another form of Euler-Lagrange equation, right. So let me now start with the so called Hamilton's equation. What are Hamilton's equation? This is another form of Euler-Lagrange conditions, okay. Okay, we will see what is the advantage of Hamilton's equation soon. So now let us, to describe the Hamilton's equation, we start with the functional So let J be a functional, let J be a functional such that J of Q bar is integral from T0 to T1 L of T comma Q bar dot d dt, and where my vector Q bar is Q1, Q2, Qn, and my function L is the Lagrangian, L is the Lagrangian function, and my vector Q is, let me term this as Q is if, so I say that if Q is a smooth extremal, if Q is a smooth extremal, then it must satisfy the n Euler Lagrange equation, which is partial L partial Qk dot minus partial L partial Qk. This is set equal to 0. If Q is a Lagrangian, if Q is a smooth extremal, then it must satisfy the Euler Lagrange equation. Let me say this relation as 1. So now I am going to use Legendre transformation and introduce new variables. So introduce the so called conjugate variables, which are P and H, conjugate variables. Okay. So I see that my Pk, which is also equal to partial L partial Qk dot, Pk is partial L partial Qk dot, is the generalized momenta. Okay. Okay, and we write down, well, we can set, as we have just mentioned few slides back, we can always invert this relation to find Qj dot in terms of Pj's. So this relation can be inverted to give me Qj dot as a function of T comma Qj comma Pj, right. Okay. So my Hamiltonian, so this is my first variable. So my Hamiltonian h of t, I call this as my Hamiltonian function, Hamiltonian function h of t comma q bar comma p bar is summation p I q I, right, p I q I dot minus L of t comma q bar dot. Okay. Now let us see some necessary derivatives out of this Hamiltonian. So we see that if we differentiate Hamiltonian with respect to Pi, the Pi only appears, Pi is an independent variable, it only appears in the first sum I from 1 to n. So the derivative of h with respect to Pi will give me Qi dot, and the derivative of h with respect to Qi will give me the derivative of L with respect to Qi with a minus sign, because Qi appears only in the second term. So I see that partial h partial Pi is equal to Qi, and we also see that partial h partial Qi is minus L minus Qi, that is from the definition of Hamiltonian, but this is using chain rule, this is also equal to partial L partial Qi dot of d dt of this quantity, right. So the last is via the chain rule. Okay. Okay, so notice that this quantity is nothing but Pi, our definition of generalized momenta, and so I get that this is also equal to Pi dot, right. Well, the first one is this. Okay, so which means, so from these two I see two relations emerging, that Qi dot is partial h partial Pi, and Pi dot is is, well, I have a minus sign here, so minus. So is minus partial H partial Qi, right? So that is my set of two equations, and I call this as my Hamilton's equation. Okay, so I call this as my, so these two are the relations that we were after. So the idea is to derive the Hamilton's equation, we start with our Euler-Lagrange condition. From there I transform those equations into the conjugate variables, and from there I derive the necessary equations, which are these two set of equations. Notice now we have two sets of decoupled equation for each I, rather than having one coupled equation in terms of in Euler-Lagrange condition. So what we have now is, so by the way, this is Hamilton's equation, or also known as the canonical Euler-Lagrange equations in generalized coordinates. Okay, and we see that these are n Euler-Lagrange differential equations, right, which are now, so for I equal to 1 to n, so the n Euler-Lagrange differential equations have been converted into 2n first order differential equations, 2n first order differential equations. So, and also to note that the derivatives of, with respect to the derivatives of q and p have been decoupled, right. So in this setup the derivative have been decoupled. So this set of equations are quite easy to solve and comparatively easier to solve than the Euler-Lagrange equation. Okay. So then finally I end this discussion by mentioning that the solution that we obtain, so the solution that we obtain, q bar comma p bar, is a unique solution. So let me call this description by 2. So is a unique solution to 2. It's a unique solution to 2 provided the Hessian matrix has a non-zero determinant, or this sort of a Hessian, del q1 dot to del qn dot by partial p1 to pn. This Hessian is non-zero. The determinant of this Hessian is non-zero, right? Okay. Let us quickly look at how to use Hamilton's equation in finding the extremal of a functional. So the example that I have in mind is that of the simple pendulum. So again we have a pendulum, standard blob of mass m, which is hanging by a rope of length L. So this is my rope of length L, and the angle that it subtends, let us say that this is phi of t, right, and let us say the position coordinate is x comma y at any point of time, and so this is m. So I am not going to write down the statement, but rather state the functional directly. So in this case I have to minimize the action integral, which was described few lectures back. So j of phi is integral of the sum of the integral of the Lagrangian, which is m L square phi dot square by 2 minus m g L 1 minus cos phi, right, times dt, mgl 1 minus cos phi times dt, and we see that my Lagrangian, let me call this as A, my Lagrangian is L of t comma phi dot. This is m L square phi dot square by 2 minus mgl mgl cos, well, mgl cos 1 minus cos phi. So that's my Lagrangian, and from here before I use my Hamilton's equation to solve, let us look at the solution via the Euler-Lagrange. So recall, so that has already been done earlier, few lectures back. So recall the Euler-Lagrange machinery provided this following relation. So d dt of del L del phi dot minus del L del phi is equal to 0, and I see that this is also equal to d dt of, well, del L del phi dot will give me ml square ml square phi dot times with a minus. So del L del phi will give me plus mgl sin phi, right, and this is set equal to 0. I take the necessary derivative. I see that this is also equal to phi double dot plus g by L sin phi, right. This is also equal to 0, and we see that this is, so this is my standard pendulum equation that we derived from Euler-Lagrange earlier, okay, describing. So we solve for the angle phi. We have done that earlier. So let us see what happens when we use the Hamilton's equation, right. So now I am going to use the Hamilton's equation. For that I have to set up the conjugate variables, right. So my P, this is a one dependent variable problem. So my P is partial L partial phi dot, and by definition of Lagrangian it comes out to be ml square phi dot, right. So from here I can see that phi dot is equal to P by ml square, right. And secondly, my Hamiltonian h of phi comma P comes out to be P phi dot minus L, and from here I can plug in the value of the Lagrangian. I see that, and also phi dot, I see that this is also equal to P square by 2 ml square minus the Lagrangian, which is, well minus the Lagrangian, which after all the simplification we get the following, okay. So these are my two conjugate variables. Phi dot has been described in terms of P, and now let us look at the Hamilton's equation. Once we have Hamilton's equation, so the Hamilton's equation is partial H partial P is phi dot, and the second one is minus partial H partial phi, which is the dependent variable, is P dot, right. So from here I get that phi dot is equal to del H del P. We differentiate with respect to P, I get that this is equal to P by ml square from the definition of Hamiltonian. And from here I see that my P dot is del H del phi, which is minus mgl sin phi, okay. So then we solve this equation simultaneously. We differentiate this equation and plug the answer in the first one to come to a point that phi double dot is equal to P dot by ml square, which is also equal to minus mgl sin phi divided by ml square, mgl sin phi divided by ml square, right. So what we get is the following. So from here my equation reduces to phi double dot plus g by L sin phi, phi double dot plus g by L sin phi is equal to 0, right. and that is the same equation as the Euler-Lagrange equation. Okay. So, the Hamilton's equation in this case gives us the extremal, which is originally given by the Euler-Lagrange machinery. Okay. So, let us look at another example in which the Hamilton's principle is specially useful. The Euler-Lagrange machinery is going to give me an equation which is very, very complicated.